Aaron, I've started admitting people. I hope that's okay.
That is a huge help. Please, thank you.
Okay.
I'm busy trying to correct the live stream settings, but I think now we're good and streaming live.
Okay. I'll keep admitting.
Thanks.
Maybe I'll also go ahead and share.
Yeah.
Okay. Soon.
Hi, everyone. We're just a few minutes away from starting the discussion session today, so hang in for just a little longer. I like watching Justin and I both race to admit people.
Can you see my participants list?
No, but I see your mouse shuffle up to the right-hand corner of your screen. So I know what you're up to.
Yeah.
So Zoom doesn't make that automatic. You can't like give it a list of allowed people.
I could, in principle, maybe give a list of emails, but they have to be exactly the emails people use to register for Zoom. What's happening here is the University of Texas security settings have been set pretty high because of all the panic about Zoom bombing. So I can't change those settings. All I can do is manually admit non-UT people. All right, it's now 11:40. So what I think I'll do is I'll turn things over to Justin, who's very kindly agreed to chair this session, and I'll keep admitting people while he focuses on leading the discussion.
Okay, thanks very much, Aaron. In that case, I'll stop admitting people. And so I had this up in the past few minutes. Maybe people were reading over this. However, I wrote that last slide before today's talks, and then during and after today's talks, maybe kind of zeroed in on some more particular points. And I hope we'll have time for several of these. We certainly don't have to plan out everything from the beginning. However, I thought we could start with perhaps giving Alexandre, a chance at a proper question and comment session. So actually, Alex, are you there?
I'm here. Can you hear me?
Yes, great. So in fact, I will now stop sharing and let you put up your slides.
Okay.
And I would say let's open the floor for questions. But
Can you see that?
I think, yes, we can see. Let's let the first question or comment go to Eric Poisson.
Yeah, thank you very much. I was, I was a bit anxious because I was named in the talk and also because Alex and I have had a pretty intense correspondence in the last week. So do you mind if I share my screen?
Let me give you co-host privileges, Eric. So just 1 second. I'm fighting with a list of admittances. And here we go. There you go. All right, you now have the ability to share your screen.
Okay, thank you. Let me see if I can do it.
So I guess, Alexander, you need to stop sharing. Yeah,
That's good. Found how to do it.
thanks.
Okay, so what you heard from the talk is that Alex and his team and I have a disagreement on the value of love numbers for Kerr black holes. And what I would like to stress here is that the disagreement has to do with definition. And I would like to go back to an argument that I learned from Sam, and I'm glad that Sam is here because he's going to back me up when things get tough, about the definition-related disagreement that you can have about love numbers. So the first point I'll make is that love numbers are defined. They can be defined in different ways. Their value, of course, will depend on how you choose to define them. And the definition that you choose might reflect different personal choices from your colleagues. So let me start with the case of a non-rotating body. There doesn't seem to be much disagreement about this, but I want to point out a few things. And I'll start with the idea that what we're all trying to do here is to decompose a physical, can you see my cursor?
Yeah, we can.
Okay, thank you. So we're trying to decompose a physical solution to the perturbation equation close to a black hole in terms of a tidal field and in terms of a response function. So the idea here is that we have a basis of solutions, one we call tidal, the other one we call response. And the response is supposed to capture the response of the body under the action of the tidal field. To that, we attach a constant, and that constant we call a love number. So the issue is really how we choose to define the tidal field. So, so when Binnington and I did this work, and when Nagar and Damore did this work a long time ago, we all agreed on what a sensible definition would be for a tidal field. That's something that would be growing in powers of R. But that's not enough, because if you decide that the solution is growing, you can always add to that growing solution a bit of a decaying solution, and it's still a growing solution. So part of the issue, I mean, the only issue at hand here is what else do you impose on the tidal field to make it unambiguous? So in the definitions that we provided, we said, okay, well, we like this tidal field because for a non-rotating body, it corresponds to a finite polynomial that starts at r to the L power and stops at order 0 power in R. So it's a terminating polynomial in R. And in addition to that, it's a function that's smooth on the event horizon. The response is a decaying solution. And if you work out all the relativistic corrections, it never terminates. And in addition to that, while it's not smooth at the event horizon. Given those definitions, well, now we have a tidal field, we have a response, we have, we have the ability to assign values to those love numbers. And because we want the solution to be smooth on the horizon for a black hole, we say that the love numbers for a black hole have to be 0. Now, what I learned from Sam on this is that, well, okay, well, I like those choices for my, I like this definition for a tidal field, but Sam doesn't have to like it, and Alex doesn't have to like it, so they can make their own choices. And I think that's perfectly fine. So we can consider a change of basis. I can add a bit of a decaying solution to the growing solution and call that my favorite tidal field. Now, I'm losing some of the properties that I happen to like, but maybe Sam doesn't mind. We still have a growing solution. Now it doesn't terminate, and it's no longer smooth at r equals 2m, but that's fine. He's entitled to his choices. For the decaying solution, we don't have freedom because it has to be decaying in any case. But if we choose to make this change of basis, well, the issue now is that I'm decomposing my physical field in terms of different basis solutions. And if you do the math, which is simple, what you see is that you've shifted the coefficient in front of the decaying solution by that constant that you've put in here when you did the change in basis. So what that's saying here is that all love numbers have been shifted by the same constant C. And if you adopt this new definition for the love number, then it's no longer 0 for a black hole, because the black hole, along with everything else, has been shifted by that constant C. So that goes to say that people can make different choices of bases and end up with different assignments for love numbers. And we're all correct. We're all doing, sensible things. We're just disagreeing on definitions for those quantities. Sam had a very nice proposal to restore, to remove the ambiguity of all of this, and it's to say that what's really meaningful here are differences between love numbers between, say, my favorite model for a neutron star and a black hole. So that difference will be, of course, insensitive to that constant C. So what's going on with rotating black holes is that, well, my favorite basis would be one that's analogous to this. In particular, I would like to impose, in a rotating case, a definition for a tidal field that gives me smoothness on the Kerr horizon. And if I use this definition, then of course, my physical field, which is smooth, will agree with the tidal field, which is also smooth. And therefore, according to my definition of a tidal field, the love number is 0. Well, Alex and his collaborators don't like that definition. They have some other proposal on how to, how to pick a basis of solutions for the tidal and response. And because of that, they end up with a non-zero love number for their Kerr black hole. So to me, it's just that. There's no, there's no issue of what the correct physics is. There's just an issue of defining love numbers differently. And of course, if you adopt different definitions, you'll get different answers. The physics, of course, is the same. And the last thing I'll say is that, well, because the physics is the same, there cannot be a consequence, physical consequence, to the fact that they assign a non-zero love number to their Kerr black hole when I would assign a 0 love number to that black hole. So we're all defining things differently, but there cannot be a physical consequence to our disagreement on definitions. And that's where I think, in essence, the correspondence between Alex and I over the last week have not converged. They think there's physical consequence to that non-zero assignment. I still maintain that there's no consequence to it. And I'm not sure that we'll resolve this anytime soon, but that's my perception of the issues that were hinted at in this morning's talk. So I'll stop here. Thank you.
Thank you, Eric. And let's first let Alex comment on that comment. And if you want to share again now, Alex, of course you can.
Okay. Can you see the slides?
Yes, we can.
Okay, so I'm going to go to the very end. Yeah. So there are essentially 3 points I would like to make, which are related to what Eric was talking about. So Eric was talking mostly about an ambiguity in the definition of the tidal field and how he manages to resolve this ambiguity by asking smoothness. So there's a thing I'd like to emphasize, which is that there's another ambiguity which was pointed out by Fang and Lovelace, and later Sam expanded on this, which has to do with the linear response. Well, I mean, it's really related to what Eric was talking about, but the one important point I think that needs to be emphasized is that if you, let's say you choose, you start with your favorite coordinate system, and you have an idea of what the split is supposed to be between the tidal contribution and the response contribution. And then someone says, well, actually, I don't like your coordinates. I want to perform a radial coordinate transformation. And imagine that this new radial coordinate has a subdominant term that scales like 1 over r to some power. Then clearly, when you're going to Taylor expand this term, it's going to affect the linear response and shift the value of what you used to call the love numbers. So that introduces some ambiguity in the definition of the linear response, and therefore in the end in what you mean by a love number. So that's the point that Sam emphasized a lot in his paper. And one reason why we want to use analytic continuation is because it allows us to go around this ambiguity, in the sense that if I analytically continue this multipolar index to real values, I can perform any radial coordinate transformation I want, as long as it doesn't depend on the multipolar index, which would be completely unnatural. It will not mix the split between tidal field and linear response. I can still identify what is a tidal field and what is a linear response. And there's another ambiguity which is lifted thanks to analytic continuation, which is the one about the tidal field. So like Eric said, if I start with, so let's say now, imagine I have defined what I mean by linear response, for instance, thanks to the argument I just mentioned, but still I could say, well, the tidal field has to be growing. And if I add part of the decaying solution to that growing solution, it's still going to be growing. So it still qualifies as a good tidal field. And the way Eric uniquely specifies his tidal field is by asking smoothness everywhere, and in particular on the horizon of the black hole. And my point I tried to make in the talk is that if you use analytic continuation, you don't need to do that, because there is a unique and unambiguous split between tidal and response, in the sense that each of those two terms carries the pure asymptotic behaviors that correspond to the Newton limit I emphasized at the beginning of the talk. And so we don't need to impose an extra condition, which is our favorite condition, for instance, like smoothness. I'm not annoyed by the fact that those two solutions you obtain by analytic continuation are not smooth on the horizon, because in practice, I cannot measure any of them separately. The only thing I can have access to is the full solution. If I get close to my tidally perturbed black hole, I will only sense the full space-time, not just some part of it. So I don't need to ask a physical condition like smoothness. I don't require it for my tidal field. And I guess the most important point here is the one that Eric was talking about at the end, which is the issue of consequences. I mean, do those questions of definition have any observable consequences? And Eric was arguing that they can't. And this is why I think I still don't understand his argument. And so far I disagree. Essentially, for instance, by taking this work by Pani and Maselli, what they did is to summarize, is that essentially they took two non-spinning point particles with different masses to model an extreme mass ratio in spiral, and they looked at the Newtonian expression for the tidal deformability that you get by accounting for Newtonian tidal love number in the equations of motion and in the radiation field at the leading post-Newtonian order, which is the Einstein quadrupole formula. I hope, I'm not sure, but maybe Eric will tell, that he would agree that this effect is not ambiguous, because to get this effect, you just use Newtonian physics. And so essentially you have a unique notion of radial coordinate. So the ambiguity that Sam mentions is not relevant here. You have the Euclidean three space that allows you to define a unique notion of radial coordinate. And therefore, the effect you have in the phase, in my opinion, is physically meaningful and unambiguous. And if you take the extreme mass ratio limit, you get this effect that was pointed out by Pani and Maselli. And I think this effect is physical. I think if Lisa gives us an Emery waveform, we measure it, we should be able to extract out of the full phase this particular term, which is physically related to a non-vanishing tidal love number. So how did you get that tidal love number in the first place? Well, you did it by matching the kind of calculation we did when you perturb a Kerr black hole to an effective description in terms of an effective action that describes two spinning point particles with finite size effect, which are accounted for by this kind of non-minimal couplings to curvature. And once you have the effective action, you can really derive unambiguously the physical effect in the equations of motion, for instance. The whole point is to match this to the microscopic calculation, the one we perform, where we do a linear perturbation of a Kerr black hole. And I can't see how this is a question of definition or choice. In my opinion, there is a correct value of this love tensor here that comes from the matching and which leads to an unambiguous physical effect that could be measured in the waveform. So I hope I was.
Right. So if I can rebut very quickly, so I agree with the last point. So I agree that there's something that you can call the love number observable that you would measure in gravitational wave phase. And at least in the case of the non-rotating, in a non-rotating case, Raphael has this calculation that shows a match between, well, so I have three love numbers, one that appears in the metric, one appears in the equations of motion, and the third one that appears in the gravitational waves. So I think there's a match between the metric love number and the equations of motion or action love number in a non-rotating case. So I agree that there's an observable at the end. Whether that observable is exactly the same love number that you define or I define, well, that I don't know in the Kerr case.
So I agree in the Kerr case, it's not been proven, but I think in the Schwarzschild case, it's been proven. And so in principle, it means one can do the matching and prove that they are the same or they differ by something related to the renormalization group flow. And one can do the calculation and get the answer. And so it would be a unique answer. It will not depend on one's favorite definition for what a good love number is for a black hole.
Yeah, no, I agree with that. And I think Raphael was saying that he can do the calculation and he can tell us what the answer is.
So let's go back to Aaron Zimmerman.
Can we ask questions or no? Can we talk? How does this work?
Yeah, can you put your hand up?
Yeah,
Again?
one sec. So I'm going to withdraw my question. I think next was Alessandra's question, which she typed in the chat.
Did you want to add anything, Alessandra?
Well, in part, I think was answered now by Eric in the sense I understand that for the spinning case is not known in the sense you don't know how the love number, for example, that Alexander was describing would affect the waveform. I mean, it seems that you are saying that until this is at the moment not clear. Is it not correct what I'm saying? I mean, the conclusion of this discussion about how this is related with something that you can measure from the gravitational wave.
Right. So my understanding is that, so thinking back of the three love numbers, you have the metric love number, which I think is subjected to that, choice of basis ambiguity. There's an action love number, and then there's, the actual observable, which would be the waveform love number. I don't think there's been a calculation that does the mapping between metric to action to gravitational wave love numbers. So I think even in the non-spinning case, there's still, a question as to whether there's not a non-zero black hole love number that should appear in waveforms. And, but at least there seems to be this matching between the action love number and the metric love number in the non-spinning case. As far as I understand, there's no matching yet, that's been done in the Kerr case, and we're still far from a matching that would carry all the way through the gravitational wave love number.
Can I just add one follow-up question about this? Maybe it's a naive question, but what happens for the neutron star in the sense you are discussing the black hole, there is this ambiguity. Would this ambiguity also propagate to the case of the neutron star, in particular if it has spin, or there everything is clear?
You want to take that one, Alex?
I'm sorry, Alessandro. I think I didn't understand the question. Could you please repeat?
I was just saying whether this issue of the definition of the lab number and the fact that it's ambiguous also affects the neutron star lab number, not just the black hole lab number.
Well, my point of view is that for the same reason as in the black hole case, if you are to use analytic continuation to define your tidal and linear response in the case where you would consider a spinning neutron star, for instance, you would not get such an ambiguity, and by doing a matching calculation to an effective action, you would get a unique notion of what the love numbers are at the level of the dynamics, for instance. And
so I'll stop you here and say that I disagree because there's a lot of issues going on when you go beyond linearized spin Kerr. So when you calculate a love number for full Kerr, you're perturbing off of Kerr. If you wanted to do this for a neutron star, you would have to perturb off the appropriate external solution for that star with its own collection of multiple moments. And for each star, you would get a different collection of multiple moments and therefore a perturbation from a very different background spacetime. So to define love numbers for a whole class of rotating bodies beyond black holes, I think requires a lot more discussion and a lot more thinking.
okay. So far here, we just looked at the black hole case, which we think is interesting intrinsically by itself, but I guess well, you're way more familiar with the neutron star case, so I'm not aware of those additional complications.
So this is great discussion. As Aaron pointed out, we have hands up. First, we'll have Leo, and then we'll have Raphael. And I think it's good if this tidal love numbers of black holes discussion continues, say, for the first half of this session. And in fact, sorry, Leo, I might take my prerogative as the chair to interject my own question before yours, or comment, which is that, so, right, the baseline has to be some observable where we can measure something related to this love number. And isn't there always kind of the issue that if black holes had a non-zero love number, in fact, as has been talked about in the chat, in this effective action description, if there's a non-zero coefficient of a Riemann squared term in the effective action, doesn't that end up being almost entirely, if not entirely, degenerate with other aspects of the full fifth post-Newtonian dynamics? As in, like, we know that the contribution, for example, in the waveform phase due to a tidal love number looks just like a 5PN contribution. Can we really distinguish between different love numbers of black holes without having the rest of the 5PN calculation that has, quote unquote, nothing to do with tidal effects?
Right, and I think the answer to that is no.
Okay,
So for that particular effect, actually, maybe just a detail, but it's a 5.5 PN effect, because at 5 PN order, it would be the non-rotating love numbers which vanish, and so you get this additional factor of spin, which gives you half an extra PN order.
Right.
But so I mean, I would have to look in the eyes at this term at the level, say, of the binding energy or something like that, or ideally the gravitational wave phase, and see how it scales with mass and spin and so on, to see if, in a certain sense, one could disentangle this contribution out of other contributions. I mean, its functional form as a function of spin and mass could be such that one could extract that particular piece of information out of the phase. I mean, I could imagine that. I don't know how to exclude it from first principle, but we're still quite far from having that functional form for any spin. So,
right. So let's hear from Leo.
Hi, can you hear me?
Yes.
Okay, this is a very tangential point, but I just wanted to raise it, that I think we can see some minor evidence for Alexander's result from numerical relativity, which is that a grad student here has been extracting the shape love numbers, which of course are different from all of these other love numbers, extremely not observable. This is just describing the shape of the apparent horizon, so it's very gaugey. But regardless, these shape love numbers for apparent horizons in numerical relativity simulations seem to have the same phenomenon where Alex has had a purely imaginary love numbers, which I interpret as having a phase shift between the external field and the response. And if you look at what apparent horizons do in numerical relativity, they also have the phase shift, so that they don't look like, if you go to slide 12, I guess, the way that you drew the tidal bulge, like on a moon. Yeah, exactly, that one. That's what we think of when we think of like the ocean tides, but in apparent horizons in numerical relativity, it's rotated by 90 degrees, which is a 90-degree phase shift for the m equals 1, L equals 2 moment. So that's at least some very weak evidence that this could be a real thing.
Okay, thanks. Raphael, would you like to say something?
Okay. So one question you can ask is, for example, what we just computed, right? The scattering angle, say, from an encounter of two black holes. And then you can ask whether the tidal effects will contribute. So if you can calculate this to order 1 over b to the 6 in the impact parameter, or the scattering cross-section to omega to the 8, then you will know for sure whether you need a non-zero value. This is completely unambiguous, okay? And so I have a question for Alexander. Can you show me the term in the effective action, please?
sure, it's here. So it's a coupling between a tensor, we call it tidal tensor, and the tidal field. And I think what you're interested in is writing this tidal tensor into a combination of a spin vector, a spin tensor, and some other tensor. We didn't do that yet.
Yeah, but then how do you know this transforms properly? You want to have something linear in the spin, right?
Sure, it is linear in the spin, as you can see.
How do you get this tensor? Yeah, how does this transform?
So we didn't look at how it transforms, but I can explain to you how we go from the tidal of numbers to the tidal of tensors, if you wish. So basically,
understand how is how is this term diffeomorphism invariant?
So here the moments are the moments expressed in the local asymptotic rest frame of the black hole in this case. And so they are defined as contractions of the tetrad you've used to define that local asymptotic rest frame with the covariant tidal moments, space-time covariant.
I understand,
so
but in principle, I could transform.
You would have a tidal of tensor, which would be this object contracted with 4 spatial legs of our tetrad. So that would transform like a tensor under a general coordinate transformation, but it's tetrad dependent. And the interesting point is how does it transform in the rotation of the triangle? In that we didn't look yet.
But the tetrad, I would have thought you will use the velocity and the spin, right? Because there is no other preferred direction, right? This is an induced effect. It cannot be there unless you put an external field. So unless you pick a direction in space, which will break the symmetry, you better write this operator with S and U. And I don't see how you can do that with linear and spin.
So there is a preferred direction, which is that of the background Kerr black hole.
The what?
That of the background Kerr black hole, there is a preferred spatial direction given by the background Kerr geometry.
The spin. Yeah, the spin makes a direction. So you use the spin operator to define the direction. So you
exactly.
should do this operator with S and U and the curvature and nothing else.
And
have
I guess
thought about that?
I mean, you could have the metric and the volume form and stuff like that. Stuff
I agree.
constructed.
I agree, but I have a hard time doing it. Have you
Well,
thought about?
Work harder then.
Okay, good. But linear and spin is not easy.
Yeah, we didn't look at that yet. That's something we're planning on doing, but we haven't done it yet.
Because naively, I would have thought you cannot do it. So that's why this guy should not be there. But if you show how to do it, it will be fantastic.
Okay.
Thank you.
Yes, thank you both. Does anyone else have any questions or comments about love numbers for black holes or other objects? Yes, Chashin.
Oh, hi. Can you guys hear me?
Yes, we can.
Yeah, so I just have a quick question after Raphael. So could you say how is this lambda ABCD defined in terms of the usual spin tensor or vectors?
I think you know how to answer.
So I guess Alex, of course you can chime in again, but he was just saying that they haven't looked at that yet.
Ah, I see.
He doesn't know. Yeah.
But we haven't done it.
I see. I guess my confusion is I saw for linear in spin, this part is completely universal, so there's no room for additional operator for linear in spin order. But yeah, I haven't looked at them like careful enough. But I saw linear in spin is universal, so there's no correction at order G squared.
Well, that is, I guess, not necessarily the case. Or anyone else have a comment on that? I mean, I know what you're saying, Shashin. Like I myself have said this repeatedly that the.
But I guess ultimately a question depends on, can you write down something exactly like follow Raphael's question, what's the operator with linear in spin and two powers of Riemann?
Right. So that is, as we keep hearing, something to be looked at.
Okay, thank you.
Thank you. Anyone else? Comments or questions?
So I guess I would have I have a question. Like I I would be interested in having a sort of global opinion about how legitimate it is for this community to rely on this analytic continuation that we rely on. I mean, to us, it was so obvious that if we want to go beyond Newtonian gravity and maintain something unique and ambiguous, this is the thing to do, to keep track of the two solutions. But it seems like not everybody agrees with this. I mean, we saw a few papers which advocate this. Paolo Pani and his collaborators, Jan Steinhoff and his collaborators, but this does not seem to be universally appreciated or shared. So I mean, anyone's opinion on this is actually very, very important to us.
Any takers? I'm afraid I myself don't have anything intelligent to say.
So since no one's talking, I'll pipe in. This is Sam Grella. My opinion is it sounds scary, it sounds strange, and it seems like you should be able to just compute an observable. And so, you know, until then, I think you have a definition based on your favorite thing, which is scary to me. Eric has a definition based on his favorite thing, which I like in some ways and don't like in other ways. And, you know, we have Komar and ADM masses. They're different and they're useful, and both are used to compute observables. So I think this will be resolved when there are observables computed.
That sounds reasonable. Martin, had your hand up?
Yeah, just what exactly is being analytically continued here? That's still unclear to me. Alex,
The
can you
the
explain?
multiplier index L here is supposed to be an integer larger than 2 physically. And here we are allowing it to run in the set of real numbers such that this decaying solution for a given value of L is not buried into this growing solution, because actually this can be decaying and this can be growing if L is a large enough negative real number, for instance. So you can really separate the two solutions by allowing L to not just be an integer larger than 2. This is what we mean by analytic continuation here.
I think I still don't understand, but that maybe just me.
Let me try it differently. So physically, you would say, okay, this term really decays. For instance, L equal 2, that decays like 1 over r to the 5th. And this term's, well, it's constant for equal 2, but I mean, you get the point. And so when you look at the large R behavior, the asymptotic behavior far away from the black hole, you will lose information about the decaying term compared to the growing term. If I go back to the Newtonian problem, that would mean, asymptotically, this term can be neglected compared to that term. So you're just going to sense the tidal field. You're not going to sense the linear response of the body. But in Newton gravity, I mean, you have the exact result. So you really know what is the tidal and the response. And it's completely unambiguous, even in terms of the physical interpretation. Now in GR, there are those two issues, those two ambiguities we keep talking about. And to go around them, what we do is we say for a moment that L is not an integer larger than 2, it's a real number. That can be a negative number in such a way that this is the growing solution and this is the decaying solution. So you do all your calculations keeping L real, just like you do analytic continuation in the space-time dimension in the effective field theory framework, for instance. And so you really keep track of the tidal and response solution all the way through. And at the very end of the calculation, you come back to the real world and set L to be an integer larger than 2. Was that clear?
But, well, no, I guess the thing that confuses me is that there will be terms with R everywhere between these things as well and beyond. How are we filtering out just two things here?
So Martin, this is Mark. I'm just sitting beside Alex here. Just let me give you an example. Like Eric showed in his slides how in Schwarzschild spacetime it becomes polynomial. And so I think he deduces from that that there is no linear response term in it. There's no r to the minus L minus 3. So even in Kerr, we see this at the level of the Hartz potential. When you take L to be an integer larger than 2, you can see that it becomes, the physical solution becomes a polynomial. But if you go to L real, you can in fact see that that's a result of a linear combination between a tidal field that grows like r to the L minus 2 and a linear response term, which is r minus L minus 3. And there's a cancellation, there's an exact cancellation between the non-smooth part of the tidal field and the linear response, so that the result is actually a polynomial. But you can only see that when you go to L and L real, because whenever you go to L real, you just don't know which one dominates over the other one. There's no dominant subdominant solutions. And analytically continuing it allows you to unambiguously identify which is the solution that grows like r to the L minus 2, or that goes like r to the L minus 2, and which one goes like r to the minus L minus 3.
So you're just literally looking for solutions that have that behavior, or because the solution is some combination of two hypergeometric functions.
So okay, I have another backup slide, which is useful for this.
Yes, this is something yeah.
now it speaks to you, equations. So you have a second order differential equation, the Tokowski equation in the static limit. You can choose different bases. For instance, you can take a this smooth solution everywhere and this unsmooth solution on the horizon. And in fact, since you asked the total solution to be smooth, the full physical solution is going to be given by this. But you could look instead at another basis of solution, which you want to call tidal and response, precisely because they have those asymptotic behaviors which correspond to the Newtonian limit. And so, sorry, what was your question again? I lost my.
I think this is so. You're really just defining the response solution as being the solution that has that particular Pavlov behavior.
Exactly. We define the tidal and the response as being the two unique solutions, linearly independent solutions that carry the pure asymptotic behaviors associated with the differential equation, so as to stay as close as possible to the Newtonian definition of what is a tidal field and the linear response. In the Newtonian limit, you don't need to go to L real, because the radial part of the Laplace equation is just r to the L and r to the minus L minus 1, so you're done. But in GR, you have those infinite series, which are a problem. If you stay with L and integral larger than 2, you have all the problems we keep talking about. If you do analytic continuation, in a sense, you're back to the Newtonian setting where you know exactly what you mean by response and by tidal contribution. Does that answer your question?
I think a little bit. I think I'm still also confused, but I'm not sure that it's going to reduce any more tonight.
I think it's fair, and I hope you find it fair to say that, you know, your reliance on analytic continuation is a preference that you have that I may not share. Right?
Well,
So that's my point about personal preferences in choosing definitions for things.
But it's a preference that allows us to uniquely identify which is the solution that goes like r to the L minus 2 and which one goes like r minus L minus 3.
Sure, that's a preference.
Functions like smoothness to a field you couldn't physically measure.
So
yeah, different preferences. I mean, I don't think there's a way around that.
But you stated that the tidal solution must go, you said there's no ambiguity, that it's the one that goes like r to the minus L minus 3. And you identified that as a tidal solution because you see that it goes like r to the minus L minus 3. And what we're saying is that if we go to our L real, we can do exactly the same thing with the tidal solution as well. So every time I say tidal, I meant response, I think, before.
Sorry,
so
Eric?
identify the response solution as the one going like r to the minus L minus 3, because you can do that unequivocally when you are L integer or L positive integer. And we can do the same identification for the tidal part as well when we go to L real.
So it sounds to me like Eric wants to do the unmeasurable thing of extending to the event horizon of a black hole, identifying R with the areal radius, and you guys want to do the unphysical thing of extending to, you know, real values of L, and they're both preferences. And those of us not wedded to either are waiting and wondering, you know, which is going to be more useful.
Yeah, I guess the extremely pragmatic thing to say is that these things are already in any self-force calculation.
That was another point I
these solutions already show up.
So that's another point I wanted to raise, or a question I wanted to ask. It seems to me that when you do, let's say, a post-adiabatic self-force calculation, which is completely self-consistent, I mean, physically, the effect of the tidal field of the small body on the big black hole should be included. And so my impression is the full waveform should by itself include the contribution that we are isolating through this calculation that was done by Bani and Maseli. But this is a question I'm asking.
I think any effect, such tidal effects, would already be in the first order self-force.
Yes, it sounds like the two of you agree on that. This is a very interesting conversation. I hope it will continue. Of course, we can continue in the Slack. And Sam, did you have a last thought, or did you forget to put your hand down?
I can't figure out how to put my hand down.
Oh, looks like
I can lower it for you.
So, unless anyone else would like to raise their hand for another thought, there were many other interesting talks this morning. Any last comments on love numbers?
Can I just ask a technical question of Alex?
Sure.
Are the two solutions that you had on one of your backup slides, are these the minimal and dominant solutions to the different, yeah, on the bottom, the minimal and dominant solutions for the differential equation?
So I'm not familiar with that vocabulary, minimal and dominant.
This is, so what I said before, this is exemplified in the hypergeometric function. So they are minimal and dominant when you take L to be in positive integer. And in fact, you can see, so the physical solution is also a hypergeometric function. And you can see how so if you expand the smooth hypergeometric here in terms of for large X, and you do the same thing for the unsmooth, the tidal one for large X, and you do the same thing for the response one, you can see how all the infinite terms beyond polynomial in the tidal one cancel out exactly with the response one.
Okay, so I was just raising this because it kind of fits in with Sam's idea of, if you do a basis redefinition, then you can shift around your love numbers, except the minimal and dominant solutions are kind of a natural choice of basis for solving such a differential equation.
But if I understand you well, I think when you say dominant, I think you're talking about L positive integer. When L is just an arbitrary real number, then you can't say which one dominates over the other one.
Yeah, I don't have anything to add there.
So that's precisely why what helps us to do it.
It's precisely the point to not stay in L positive integer, so that those two solutions, you can't say which one is dominating over the other one. It's only when you set L to be a positive integer, then one will indeed be subdominant compared to the other one.
Okay. Well, thanks very much, Alex.
Thank you.
Eric, everyone, for your comments. So maybe now we are a bit over halfway through. If you could stop sharing, Alex, yep. I'll put up some more discussion.
And just to the point of the schedule, while the official end time today was still 1 o'clock, consistent with the other days, this was a later start to the discussion simply because there were so many talks this morning. This meeting's not going to end. I don't have to leave. We can continue the discussion further if it's valuable to people. This discussion is the most important part of Capra.
Okay, yeah, I can stay later also. So at this point, if I may take a chance to talk about what I hope it will be quick, a technical question that came up during Donato's talk, which was raised by Ricardo, that the static 6 p.m. part of the 5 p.m. dynamics, conservative part, has already been calculated. Can it be used? And Donato, Ricardo, are you both here? Or let's start with Donato.
I'm here.
Okay, great.
And
so, Donato,
if yes, may I have the?
Yes, I would just like to quickly say, in your own paper, Donato, you have the comment that is not gauge invariant by itself without all of the rest of the
Yes.
PM part.
For me to use this information should be cast in a gauge invariant way.
Right.
And so for this reason, I could not use until these friends compute what remains to be gauge invariant.
Yeah, and I, having looked at how that would work myself, I would agree with you. Ricardo, do you have any comment?
No, actually, I was actually asking the question because I wanted to know if people can make use of anything computed in harmonic gauge. So maybe since it's static, one can make some sense out of it in a gauge invariant way, but no, I haven't thought deeply about it.
I mean, according to our analysis, and I'm guessing also Donato's analysis of how
Yes,
this
I agree.
How this works with the PM and PN simultaneous expansions. If you start at the other end, the low Post-Minkowskian orders, and go and then keep adding Post-Minkowskian orders, having 0 and 1, etc. in place, then there is gauge invariant information in these partial Post-Minkowskian things at a given Post-Newtonian order. But not if you start at the other end. You have to have all of the lower Post-Minkowskian contributions at a given Post-Newtonian order.
That makes sense. Makes sense to me.
Okay, great. All right, let's say that's done. So there are, of course, one thing we could talk about is scattering. Scattering was mentioned several times this morning, and I hope we will have time for that. I mean, we'll try to make sure that we do. But before that, Martin brought up a very interesting point, which I have wondered about a lot myself, which is in spiral merger ring down complete waveforms from self-force. This should, in principle, be doable using the first order self-force paradigm to get like a leading order waveform, but this hasn't actually been implemented. And I'd like to ask for anyone that might have thoughts about, is this worthwhile? You know, okay, so one point is that it's often said in the context of LISA for an extreme mass ratio in spiral, you know, the merger bit at the end is like a tiny contribution to the signal to noise, and it's not so important, and we don't necessarily care about it as much. So our adiabatic evolution, that's good up until the merger ring down part, is good enough. But especially in this context of importing self-force information into other schemes, in particular ones that hope to be valid for comparable mass ratios, this is in a way the most interesting part, the merger ring down. And self-force should in principle be able to produce such a waveform. And does anyone have any thoughts on going forward with that? Or is there work that I'm not aware of that looks at this? Anyone have any thoughts? Or Martin, you might like to start by.
We've got Leor and Adam with hands up so far.
Oh, I'm sorry, I had my participants list closed. Yes, let's start with Leor.
There's something that can easily be improved. I talked to Martin about this, and this is the transition term in his adiabatic expansion of phi, the term that goes like nu to the 1/5. And so I think with moderate effort, I think Martin agrees with me, you can actually calculate that term, at least for quasi-circular in spiral. And that should improve a lot the high frequency part of the comparison. Martin can tell me if can tell us if he agrees with that.
I certainly agree, and I think it's worth pointing out that this has been done for adiabatic waveform, quasi-circular, non-spinning waveforms. So there was a paper last year by Rifat and Grafkana and some collaborators that actually build waveforms like that and then build a surrogate model out of that. So
we'll be hearing about that tomorrow, actually, from Nur.
Great. So there's somebody talking about it tomorrow. So, I'll keep my mouth shut then. But yes, you should be perfectly be able to calculate this. Sorry?
So, Adam, would you like to say something, Adam?
Sure, yeah. I was going to mention the same paper by Scott Field and collaborators that Martin mentioned at adiabatic order. At post-adiabatic order, Jeffrey Compere and his PhD student are working on properly matching transition region expansion to a 2 timescale expansion.
Okay, great. So there is indeed work underway. Any other comments on such things?
So will that, for self-force calculations then, in the end, will that be time domain codes, or is it possible that what you mentioned, Adam, some kind of matching of timescales is going to allow for the more, I guess, established at the moment frequency domain methods?
Yeah, I would imagine doing a matching between them. How do I lower my hand?
It should be in the same place.
Yeah, it's the same place you raised it. I think you may even just click on it again, but
So if I raise my hand twice, I lower my hand.
Exactly. The host can also lower it. So
thanks.
Can I quickly ask, just to clarify, when I said can be calculated at the adiabatic order, I meant analytically. Is that what you meant, Martin? I'm not sure that's been done.
So the thing that hasn't been done is actually calculated properly as it would show up in a multi-time scale analysis.
Yeah, that's the kind of thing.
So what has been done is obviously the stuff that has been done in the Ori Forn and the Alessandro Bernardo de Moor papers, where they calculate what the jump should be towards the punch, which is very similar to how you would introduce a resonance transition as well. And these things seem to be closely related in how you would actually implement things.
So that hasn't been done yet.
But I don't think, yes, it hasn't been done in the form where you actually just have a term that is proportional to mu to the minus a fifth that just shows up in that expansion. And I think when you do it properly, it might actually just show up as a delta function or step function, and mu to the minus fifth at leading order.
Okay. Well, thanks very much, Neil. Is someone speaking? I was saying thanks very much, Niels, and everyone for the paper links. Those are very useful. So, if there are no other thoughts about IMR, waveforms for self-force, so we could move to scattering, and why do we care about that, and why is it interesting for self-force now? And I could just start by saying, so it was mentioned several times this morning, in fact, with some confusion, which should have been cleared up in Donato's talk, but just to make sure, let's see. So this claim was mentioned several times that the scattering angle function, which we assume is a well-defined thing, and I hope we will come back to the point that Sam raised, but we imagine a scenario where we can picture at infinity, we have flat space-time. And yes, in fact, at past and future infinity, it's not the same flat space-time necessarily, but if we just ignore that for a moment, and we focus on the conservative part of the dynamics to the extent that this can be well-defined. And it is very well-defined in the post-Newtonian expansion and perhaps also in the post-Minkowskian expansion, although that, I would argue, is still less clear. At least at low orders in the post-Newtonian expansion, there's a conservative part of the dynamics, which corresponds to a Hamiltonian, the complete gauge invariant information of which is in this scattering angle function. And then there's this very important claim that was mentioned several times today, that this scattering angle function, it depends on the impact parameter, it depends on the relative velocity at infinity, it also depends on the masses, but it has this very shocking, I would say, dependence on the masses, especially when you compare it to previous ways of looking at the same results, like our classic post-Newtonian Hamiltonian at 0 pn or Newtonian order with the kinetic and potential energy at 1 pn, at 2 pn, etc. At each increasing post-Newtonian order in this form, we have one additional power of the mass ratio. So the red terms would drop out in the test body limit. And yeah, in this counting, again, importantly, we already have nu squared at second post-Newtonian order. But a lot of these recent developments that were mentioned today have to do with the fact that if you go away from that gauge-dependent function Hamiltonian, you go to this scattering angle, it has this very surprising property that when expressed in terms of these good variables defined at infinity, impact parameter and velocity, at the first and second orders in G, it is essentially independent of the mass ratio. And so this first and second post-Minkowskian order information for arbitrary mass ratios is encoded in the test body limit. And if you go from the test body limit to first order self-force, first order in the mass ratio, that in fact gets you the complete arbitrary mass ratio answer for the scattering angle function, which again encodes the complete local and time conservative dynamics up to the fourth order in G, or 4 p.m. order. And the translation, so this has all orders in V in principle, of course. So far, this function, so these functions are known from the test body limit, all these 4. This one, an answer to all orders in V, has been given from amplitudes calculations by Zvi Baron et al. And for example, a collaborator on that paper, Cha Shen, is here with us now. They gave an answer for this term to all orders in V, which then gives the complete third post-Minkowskian dynamics, which encapsulates, I'm not writing this here, but the second post-Newtonian order. So to a given post-Minkowskian order contain, when you re-expand in post-Newtonian, it has the complete that many -1 post-Newtonian dynamics. And so the point about which there was a question or confusion this morning was, okay, so 4 p.m. we get from first order self-force. I haven't drawn it here, but the next 5 and 6 p.m. terms would come from second order self-force. And that would contain the complete 5th post-Newtonian. So if we had complete 6 p.m. from second order self-force, we would have complete 5th post-Newtonian. And it's very interesting how that is the next frontier in post-Newtonian calculations, at least of the conservative dynamics. Okay, so it's 5 p.m. that we could get from second order self-force, not 6 p.m. However, I would actually like to back up and say, so the fact that this is true, where does this come from? Well, this statement, or a proof of this statement, was given in a paper from December last year by Thibaut Damour. He gives a rather convincing argument based on the structure of the post-Minkowskian expansion, Poincare symmetry, dimensional analysis, etc., which I would venture to say is very much perhaps influenced by or inspired by, or maybe he already had all of these ideas before amplitudes were involved. But this kind of structure that we see here very much corresponds to what has developed as the way to compute these things from amplitudes, scattering amplitudes calculations, which maybe we could hear something from Chashin about if he wants to say something. But in any case, I would say...
Sorry, can I make a comment? These are just the Feynman diagrams. These are the same Feynman diagrams we're writing now. This is not deep at all, right?
Okay. I mean, in one sense, it's not, but you have to admit that in the post-Newtonian...
Why this works is partial, because up to 2 p.m. is just 1-point functions. So this is just the way you write the diagrams, right? The insertions of the sources, right? This is nothing else, right? Anyway, go ahead.
Okay. Well, I was going to say I'm not, so Damour's argument is rather convincing, but, shy of actually doing the calculation, I would say it's not 100% clear that this will in fact hold. And
sorry, why not?
Again,
you have to write Feynman diagrams, and you see how the G's comes with M. I have the M center in the calculation.
Okay.
But you see it yourself. I mean, just the same diagrams you wrote for the amplitude are the same diagrams we write to do in the sources, right? You don't need to do anything fancy.
Okay. So
sorry, my kids are right.
No worries. But it sounds like Raphael is convinced that this does in fact hold.
But I mean, you can ask Chashin or Michael who are here, right? They will tell you the same thing. You can do this with Feynman diagrams. It's not amplitude. I mean, the amplitudes give you the integrands, which are easier. I give you a bunch of Feynman diagrams, each one scaling with what you wrote in there. And we are now actually finishing the 3 p.m. Hopefully in the next couple of weeks, we'll put it out. But it's exactly the scaling that you get from the Feynman diagrams, right?
Okay. Chashin, are you still here? Yes, it looks like you maybe.
Yeah, so I think from Feynman diagram, it's not just based on the topology of Feynman diagram, it's not immediately obvious that you can get Damour's result. Although I think based on some dimensional analysis, some counting, you can still get the result from Damour.
Sorry. I mean, I don't know what Damour result is, but what he wrote in here is just the scaling of the insertion of the sources, right? How the M's, M1, M2, and so on enter.
Right. But you need to look into the vertices slightly more carefully than just looking at the diagram itself.
Why? What could go wrong?
Oh, I just mean, just for example, let's just talk about order G squared. So even the order G squared, the Feynman diagram looks like a test particle case. You just have 2 sources, but you need to know slightly more about, say, the 4-point vertex, for example. like the two graph down interact with the wall
You
line?
need the, no. You don't need the 4-point vertex.
I mean, for the 1pn case.
No, you don't need it. You're talking about the 3-point.
No, I mean the two graph down interact with the wall line.
Oh, that guy is not there.
Sorry, why not?
No, because you can use the Polyakov action. This is the magic, right?
That's true. That's true. Yeah.
So if you look at our diagrams, our power counting, this is trivial. And it just comes from the fact that you're using the Polyakov action. And just it's just vertices, that's all, right? So there's nothing else.
Okay.
Sorry, I should have just said that. But yes, from the scattering point of view, right?
Yeah.
It's not the potential. No, if you're talking about the potential, it's slightly trickier. You can get the same, but it's slightly trickier because we know how to go from the chi to the potential now, or to any observable. But for the angle, we found that you don't need any wall line nonlinearity. So that simplifies my life a lot. In fact, I can get your 3 p.m. result now much, much faster. We almost have it. We have the arc cinch exactly on the money. And we have obviously the Schwarzschild piece and so on. We are a little, okay. We think we got it. I think you're right. But this scaling is trivial, okay? Nothing fancy, super trivial.
Okay. But its consequences, which were previously unrecognized, are undeniably useful.
I will give you that. I give you that. Yes.
Yeah. And so that's it. So Raphael's convinced, and if I can just ask actually one more time, Choshin, were you saying it's not immediately clear from your amplitude's perspective? For example,
relatively clear, but it's not like just looking at diagram. Just looking at diagram itself is not sufficient, I think, because you don't get there's no free lunch. Just like the more he needs to use dimensional analysis, Poincare symmetry, you still need these ingredients.
Yeah.
Like from diagram itself, it doesn't give you that.
But you don't actually have a doubt that this is true at 4 p.m.
I'm relatively optimistic. Yeah, I think I'm confident.
Okay. That's good. And hopefully also with spin, because I and my collaborators have already stuck our neck out on it being true, as Andrea was discussing earlier today.
So Adam had a hand up.
Oh, yeah, sorry, I'm not seeing the participants list always.
And then Lior.
Please, Adam, yes.
I'm quite confused about why there's any complexity involved. I mean, so I wouldn't phrase it in terms of Feynman diagrams like Raphael, but you know, you just write down the PM expansion straightforwardly, and you just get the scaling. Just classically, just straightforward post-Minkowski.
Yeah, like just like Thibault outlines in his paper.
Exactly, yeah.
Yeah.
Yeah, so yeah, we read it in the group recently. It was disappointingly trivial. In fact,
yeah,
I can't see any problem with this really. If you do dimensional analysis and you use this symmetry of exchange of the two masses, you immediately get this result trivially.
Right.
So what you mentioned that you have some suspicions about it. What are they?
I don't really know. I'm just I just want to be extra skeptical. And, so an important caveat here is, right, that this is not, in fact, everything. This is the local part. As Donato was, I seem to have an echo.
I think it was coming from Lior, but Lior just muted.
Okay. This is, in fact, just the local part of the conservative dynamics. So even within the conservative dynamics, there's this non-local local split, as Donato discussed. And he also emphasized, however, that the non-local or tail parts are in fact the easy parts to calculate, even from a direct post-Newtonian perspective.
In principle, my friend.
In principle, yes.
Because the expansion in the inverse eccentricity is tricky and not so simple as the one in the eccentricity. I mean, I mentioned that there arise integrals which can be done only numerically after many days of mathematical working.
Right, yes. But the machinery behind it was standard post-Newtonian theory. And that's not where you needed the input from self-force.
Yes.
Right. But knowing these non-local parts directly from post-Newtonian, which again start to become an issue at the fourth post-Newtonian order, as he told us, then one can match simultaneously between your effective Hamiltonian and self-force results, particularly for the redshift, as Donato showed us. And then you assume, or you use this proven, I guess, behavior of the local part of the scattering angle. And that allows you to get this new information that Donato told us about. Now, I have some other important points here, but before I bring up my favorite thing, Ben, and actually we technically only have 2 minutes. So Sam, are you still here, Sam? Gralla?
I'm here. Yep.
Great. So as you brought up this morning, this whole paradigm of imagining that we have, okay, going to scattering is great because we can go to infinity and things are simple at infinity. But we're kind of ignoring what we should know, which is that, okay, maybe gravitational waves come out in between this flat space-time in the past, flat space-time in the future. They're not actually the same flat space-time in some way of speaking. And, how do we think about that so I said earlier, that people are not thinking about that. And, I can't speak for the whole world, but for, let's say, myself and my collaborators, we just work from the perspective of post-Newtonian results where one can cleanly split out this conservative and dissipative part, and furthermore, this tail and non-local part. And I think, in fact, that might be an important point here, is that could it in fact be that these tail or non-local parts in the PN terminology are related very much to things like super translations or BMS ambiguities that could be happening, affecting even the definition of what do we mean by scattering angle. Lior has his hand up. Please say something, Lior.
Yeah, so if you're thinking about this, if you're thinking about the first order self-force, first order perturbation theory, the space-time, the conservative space-time is exactly time symmetric, right?
Yes.
So in that case, I don't see a question, right? Is it acceptable, Sam? Or Aaron?
I had the same point. I think I was going to say that I'm not familiar with these scattering calculations, but sorry, I had to mute you, Lior. But it seems like they're not accounting for radiation emission during the scattering process, right? It's just the relativistic corrections to the interaction as they scatter off each other. So in that case, it's like one of these conservative calculations where you ignore the gravitational emission sector, you do a calculation in that sector, imagining there is no radiation, and then you don't have to worry about these things. Is that correct?
That is definitely correct.
Yes. Yeah. So in self-force calculation too, it's you can identify the conservative piece unambiguously, and then your you know, your infinite past is exactly the same as your infinite future in the scattering problem.
So, but what about the tails? I mean, they are part of the conservative dynamics. These so-called tail.
Yeah, you get the entire thing in the cell force.
Right.
In the cell force calculation.
From the conservative part of the cell force calculation, as you were saying, where you have a truly time symmetric space-time.
Yep.
Right. And you say there should be no ambiguity about BMS, etc., at the different infinities.
Yeah, I don't think so.
Okay.
Yeah, so it's not that there isn't radiation, but there is the same amount of radiation, you know, in the past and in the future, and so there's time symmetry.
Right.
And, yeah, I don't see what the problem might be at this level of first order linear calculation. So I think if we're talking about calculating this 4 p.m. term in your expression, then using cell force, there shouldn't be a problem there.
Right.
Yeah, this one here, this is the thing that Ellie wants to calculate, right? The last term at the bottom.
So when people talk about the scattering angle as this useful thing, a lot of people are apparently focusing on, they mean the scattering angle of part of the, it's not really a true observable in that you just send two black holes at each other and see what angle they come out. Is that right?
That is definitely right. And this is something, yes, that needs to be emphasized. This is not actually unobservable. Even if flat space-time at infinity, pretending it's all the same flat space-time, even if that's worked, this is just part of something physical. It is missing radiation, yes. And that is something that very much needs to be addressed within this, as it was called today or yesterday, the scattering revolution, and this post-Minkowskian approach. Something that is very much missing. A next step is, okay, what is the complete physical answer? Let's say at third post-Minkowskian order, because it seems pretty clear now that, in fact, for, you know, so this scattering angle is in fact best thought of as like being related to the change in momentum, let's say at infinity. And the change in momentum, I mean, they're basically equivalent at the first couple of orders to the scattering angle, but so what I'm trying to say is there is no contribution to the impulse or change in momentum at order g and order g squared. I mean, as far as I know, this isn't like published anywhere that this is said. No, sorry, I take that back. I think, in fact, Westphal, who first derived this result back in 1985, the second post-Minkowskian contribution to the scattering angle. I think, yes, in fact, he did say that at order g cubed is where you will first have radiation. And so at this order, precisely the one that was computed by Bernadotte, is where this stops being a complete physical observable because we know we're missing radiative contributions here. These are something that self should also be able to get.
Can you hear me? Yeah.
Yeah, sorry.
You say to the sympathy part.
Go ahead.
Okay, this is a little complicated.
So Leo, yeah, let's have Leo, then Raphael.
Okay.
Yeah, just to say that in the surface calculation, you automatically get the dissipation as well, first
Right.
order. But then you have to start worrying about how to compare the past and the future. That is true.
Okay, so Raphael?
Yeah, you're talking about the dissipative part, not the conservative part of the radiation, right?
Yes. Or let's just say I want the complete.
But you can imagine doing this very softly, so that the radiation is a small effect. So we're not PMing here, we are PMing. So
Right.
that dissipatory part, I'm with you that at 4 p.m. you cannot get around the conservative piece, but the dissipatory piece, I think I can just not see it. I can just scatter planets, okay? And I could do this without caring about the radiation reaction if I do it very softly, right? And I can measure that. Up to some soft factor, okay, fine. But it's not PN, right? It's not a 2.5 PN effect that you're missing. We are not PNing, we are PMing. You can go as low as you want.
Yes.
So I think there's a well-defined way to define some observable here. Okay, you have to put inclusive, the soft radiation, fine, but that should not be a large effect. Now, for the conservative part, I agree, it's a little tricky, even though it could be a very small effect as well. Formally, it does start at 4 p.m. So you might want to include it. Anyway, that's just the fact that it's not PN. And PN, I agree with you, you cannot ignore radiation reaction. You're spinning around, right? It's very different. So there's a period theorem that tells you how fast you're going. But here they're independent, right? Anyway.
Okay.
Can you not always, choose conservative boundary conditions and make your system conservative and time symmetric, even in PM? Naive question.
I'm very glad you brought up that question. Actually, before I say anything, Chashan, please give us your thoughts.
Oh, yeah, I just want to add a comment that, so technically, even though we say we're doing post-Minkowskian or ordering velocity, but I think technically we're still using a so-called potential region or the near zone. So the radiation effect, strictly speaking, is not included. So like, for example, in order to import the results from Salesforce, that's indeed something pretty tricky. So even though we sum in velocity, it doesn't mean that we capture all the radiation effect, because we only consider near zone or what we call the potential region so far.
But can I make a comment?
Go ahead, please.
Yes.
No, what I'm saying is that here you can, because we're doing the calculation with the cell force, okay, you do it partially numerically, but as I don't know if Leo or Adam said, you can set up the boundary conditions to make it conservative. So you can ignore the radiation for sure. You cannot ignore the tail effect that you have to put. And that's why Adam et al. Having this problem comparing with the binding energy, because it's unclear what is it we're comparing for the conservative part that you can extract from the cell force. You can formally define a conservative energy, and in fact, they have done it. The point is that at second order, you have this problem with the tail that if I understand correctly, I'm not an expert at this at all, I'm ignorant, those two are not agreeing with each other. The binding energy from cell force to second order and ours. So there's a disagreement there that could be caused by this issue. But you could set up boundary conditions to make it conservative. That you can do by hand. Now it might be not physical, but you can do it just to compare.
So about these boundary conditions, if I can ask you again, Lior, for example, I mean, so I like at infinity, say we want to have, instead of outgoing radiation, we want to have essentially a standing wave or equal amounts of ingoing and outgoing radiation. Or is that a roughly accurate statement?
Yes.
And what about
linear order? Yeah, linear order.
Let's say just a linear. Let's say we're thinking about a first order cell. So what about at the horizon? Do we also need to change the boundary conditions there? So I guess.
Yeah, well, there will be. Yeah, well, yes, you have to set time-symmetric boundary conditions on the past and future horizons as well.
Okay. Do you know of any literature where this is discussed, like how that would be technically implemented, or if you can even just say it in words?
Yeah, so you can choose your solutions to Tukowski equation in the appropriate way, but the way we do it is we use a trick that is based on orbital symmetries. When you have a geodesic in Kerr, it has this nice symmetry that Mino pointed out many years ago about the periastron. And so you can construct the conservative part of the cell force by looking at combinations of cell forcing points that are the same radii on either side of the turning point. So the plus combination of certain components will give you the conservative bit, and the minus combination will give you the dissipative bit, and the other way around for the other components. And so you can actually solve it with retarded boundary conditions that you would normally. And then after you've calculated cell force, you can construct the time symmetric part of it using this orbital symmetry trick. That's how we do it in practice. So we don't actually change the boundary conditions. But I'm not sure if you ask about how we do it in practice or about the matter of principle.
Yeah, I'm slightly disappointed by your answer because so you're exploiting the symmetries. Sorry, Lior, if you could mute yourself while you're not talking, that might help with the echo. Thanks. Oh, and yeah, so you were using the basically the reflection symmetries of the geodesic orbit, the source. So therefore, like bypassing this issue of actually changing boundary conditions. But let's say, what if you wanted to define a Green's function? So no, we're not going to specify a source, but we want to say replace the retarded Green's function with some time symmetric Green's function, if that makes sense, where we might have to change the boundary conditions both at infinity and at the horizon. Does that make sense? Or would that?
What we do is precisely equivalent to taking the half retarded plus half advanced Green's function.
Okay. Oh, sorry, Raphael, you have your hand up.
Yeah, I have a question for Lior and Adam. What is happening with this binding energy? I don't understand why you guys say that it's not the same and this is ambiguous, so the definition, and we're defining different things. Can you clarify this?
So this is only at second order.
Yeah, second order, yes.
And basically, I haven't looked at that again since I spoke to you by email a long time ago, 8-9 months
Some time ago, yeah. I was wondering whether there was a new thing.
No, so I can't remember if I spoke to you after following what seemed like a good lead, where it did seem like I could go into the explicit calculation of the PN binding energy and potentially split things up and find the 4PN term that we were disagreeing on. But I never actually did the calculation.
I see. Because if
So
we're going to go back
to this,
because we're saying about using cell force to compute something gauge invariant, and if we compute gauge invariant observables like the binding energy, and we don't even agree in the post-Newtonian, so how are we going to trust that we understand what we're doing, right? No, I mean, how are we going to use your results or our results to help one or the other?
Yeah, so if at first order you don't have this issue.
Understood, yes.
If we want to use second order results to fix what order
PM.
was it? PN?
PN or PM, you can do both, yeah.
Yeah, so for 5PN, you would definitely have to figure out what is the exact relationship. Otherwise, yeah, you can't just straightforwardly read off one and put it into the other.
Okay, so what about you guys doing the scattering angles?
So again, at first order cell force, there's no problem. At second order, I think using scattering would actually be easier for us than using bound orbits.
Okay.
The one trouble with trying to set up a completely conservative system at second order, like we could do what Moore said that he thought we should do, which is use fully conservative boundary conditions at first order and then use fully conservative boundary conditions again at second order.
Uh-huh.
Now the problem with that is for bound orbits, nothing converges if you do that. All your integrals diverge. Because the standing waves at infinity mess things up. But we could say, okay, let's define, we can still find some solution. It's just what boundary conditions are you imposing on it? Because you can't just integrate your second order source against the half retarded plus half advanced Green's function. You could integrate it to some finite region and then add a homogeneous solution, but you don't know what homogeneous solution to add in order to compare to post-Newtonian or post-Minkowskian. But you could say, okay, let me choose the one that you would get from scattering and do analytical continuation. But then that would require us to do the scattering calculation. So I think it would actually be easier to just directly do the scattering calculation.
Indeed.
And I think probably the easiest thing for us to do would be an analytical expansion either in PN or PM, but it's obviously simpler in PM.
Yeah,
of the second order equations. And rather than trying to do a fully numerical second order scattering calculation, which would be tough.
I see. Well, it's a very interesting problem. I would encourage you to do it.
Yeah, just too many
At least to learn that Adam and I just wrote a research proposal about it.
Good.
So if the referee is sitting here in the audience, you know what to do.
I'll give you the money, but it's not me.
So when you say like expanding the perturbation equations themselves in, say, post-Minkowskian, so like say expanding the Tucholsky equation itself in post-Minkowskian, is that what you mean?
Yeah.
Kind of. Okay. Yes, that sounds very worthwhile.
Essentially just becomes a series in capital M.
Sounds very
Can I say something quickly, Justin?
Please.
There was a question. There was a question at the end of Ollie's talk, and I wasn't sure if it was, you know, it was not enough time to discuss the details. But so what we are planning to do is to get the full cell force. So all powers of all PM terms are in it, but of course to linear, just a linear term in nu. I'm talking about the expansion of chi now, the scattering. So we'll get that numerically, but presumably to high precision. And from that, we're going to fit out the PM terms. And hopefully we'll get enough accuracy to get the 4 PM term at least. So that's the one that's not known yet. So that's one approach. So fit PM expansion to the numerical data.
So can I ask a question about that?
Sure, yeah.
So you would use the physical boundary conditions, basically the retarded Green's function, if you will.
Yes, that's what we do. Yeah.
Okay. So
we have the dissipation on top of that for free. That comes with our calculation, but we are going to put that aside for the sake of that calculation.
But I guess you know how to do that. You're saying how to put that aside.
Oh yes, yeah, that's the orbital symmetry trick that I just described.
Right. Okay. Good. Yes. Please continue.
Yeah. So that's one sort of one avenue. Another one is to expand. I think that was the question during the talk, to expand in advance in PM and then try to do it analytically. And so that's the thing that Adam was talking about now, and possibly we can go with that to second order. So that's a different approach. That's it.
Okay. That sounds very promising. So, Aaron, when should we aim to close this out?
I think the discussion has now been 2 hours, so this is a reasonable place to stop it if we have sort of closed off the major discussion points.
That sounds good to me, unless someone raises their hand very quickly. And let's say time's up.
All right. Well, a huge thanks to Justin and to everyone who was here. Let me just say that there's going to be a slight adjustment to the schedule tomorrow to make sure we accommodate the LIGO Virgo webinar that's going to discuss GW 1908-14, the newly announced detection of a mass ratio approximately 10 system. So I'm just going to send an email out about that right after I get off this call. Adam, you have a question or a comment?
Yeah, quick question. In the recording of this session, does it also record the chat?
The YouTube does not, but I have been recording these through Zoom, which should dump the chat log onto a cloud-based service that I haven't yet interacted with. So if there's a desire to make the chat available, I can try to figure out how to do that.
So just this chat in particular had a lot of discussion in the
Right.
chat.
Well, just in case, what I'll do is I'll literally copy the entire chat log to a text document.
Yeah, there's a save button, I think.
Save chat, there it is. Chat saved. All right, so I've saved the chat, and so that'll be available one way or the other. But also, like I said, I think I have the full Zoom call being saved to Zoom.
Perfect, thank you.
Okay, so I'll see everyone again tomorrow, bright and early for the US, at a reasonable time for everyone else, and in Europe at least, a very unreasonable time for those in Asia and Australia. Thank you all, and have a great rest of your day.